Hello everyone, and welcome to the second part of the lecture videos on line integrals of scalar fields. The first part dealt with line integrals with respect to arc length. If you have not yet seen that video, I suggest that you view it first. In this part, we will talk about line integrals of scalar fields with respect to the coordinate variables x and y. We start with the following definition. Let f be a function in two variables x and y that is continuous on some region that contains a smooth curve C, where C is parameterized by the vector-variant equation R of t, whose components are x of t, y of t, and with parameter t in the closed interval ab. Then the line integral of f along C with respect to x is given by the limit of the summation of f of xi star yi star delta xi, where the sum runs from 1 to n, and the limit is taken as n approaches infinity, provided that this limit exists. Take note that the only difference of this line integral from the line integral with respect to the arc length s is that instead of delta si, what I have here is delta xi. Their notations are also almost the same. Instead of ds, what I have here is dx. The line integral of f along C with respect to y is similarly defined. Instead of delta xi, what I have now is delta yi. For the notation, instead of dx, what I have here is dy. I think we will all agree that we do not want to evaluate these line integrals using these limit definitions. Just like the line integral with respect to the arc length, we will write these line integrals as definite integrals with respect to the parameter t. And we see that in the next remark. To compute for the line integrals of f of xy along C with respect to x and with respect to y, all we have to remember is that the differential of x dx is x prime of t dt, and the differential of y dy is y prime of t dt. Hence, we are able to write both line integrals as definite integrals with respect to the parameter t. For the line integral with respect to x, we have the integral of, we express x and y in terms of t, so we get f of x of t, y of t, and we replace dx by x prime of t dt. And since the parameter t is in the closed interval ab, then the limits of integration will be a and b. Similarly, the line integral with respect to y is the integral from a to b of f of x of t, y of t, and now we replace dy by y prime of t dt. For the next remark, whenever we have the sum of the line integral of p of xy dx and the line integral of q of xy dy, both line integrals along the same curve C, then by convention, we write it simply as the line integral of p of xy dx plus q of xy dy along the curve C. Now, we are ready for an example. In this example, we are being asked to evaluate the line integral of 3y dx plus 4xy dy along the curve C, where C is parameterized by r of t with components 1 minus t squared and t with parameter t in the closed interval negative 1, 2. Keep in mind that to evaluate this line integral, we need to write it as a definite integral with respect to the parameter t. Hence, we have the integral of 3 times, your y here is t, so we write t times, since x here is 1 minus t squared, then dx is equal to negative 2t, which is a derivative of 1 minus t squared, multiplied by dt. So, we write here times negative 2t, and we write dt at the end of a definite integral. Continuing, plus 4 times your x is again 1 minus t squared, and your y is t. Here, because your y is only t, then your dy is equal to 1, the derivative of t, multiplied by dt. And hence, this is now your integrand. You are integrating with respect to t. And since t is in the closed interval negative 1, 2, then the limits of integration are negative 1 and 2. All that remains is to evaluate this definite integral with respect to t. Simplifying, I get the integral from negative 1 to 2 of, simplify, I get negative 6t squared plus 4t minus 4t cubed dt. Integrating term by term, I get negative 2t cubed plus 2t squared minus t to the fourth, evaluated from minus 1 up to 2. At t equals 2, I get the values negative 16 plus 8 minus 16 minus, at t equals negative 1, I get positive 2 plus 2 and minus 1, which simplifies to negative 27. And that is the value of your line integral. We end this video with the following remarks. Recall that minus c is exactly the same curve c, but oriented in the opposite direction. For line integrals with respect to arc length s, we have seen in the previous video that the line integral of f of xy ds along minus c is just the same as the line integral of f of xy ds along c. Before we reveal the result in this case, let us recall the definition of the line integral with respect to x. Note that if this line integral were along minus c instead, what would change on the right-hand side are only the delta xi's. In fact, the delta xi's that you have for the line integral along minus c is just the negative of the delta xi's for the line integral along c. This implies that the line integral of f of xy dx along minus c is now the negative of the line integral of f of xy dx along c. And similarly, the line integral of f of xy dy along minus c is also the negative of the line integral of f of xy dy along c. The next remark tells us that line integrals with respect to x or y are independent of the parametrization of the curve. If you recall, the same result holds true for line integrals with respect to the arc length. Finally, if c is not necessarily smooth, but a piecewise smooth curve with disjoint smooth components c1, c2 up to cn, then the line integral of f of xy dx along c is just the sum of the line integrals of f of xy dx along the smooth curve c1, c2 up to cn. Similarly, the line integral of f of xy dy along c is just a summation of the line integral of f of xy dy along ci, I running from 1 to n. Take note that this property also holds true for line integrals with respect to arc length. This ends the second video of our lecture. In the next part, we will again look at line integrals with respect to arc length and with respect to coordinate variables, but this time of curves in three-dimensional space. See you in the next video.